We have already discussed some observation-based papers that have shown that the parts of the Atlantic meridional overturning circulation that are monitored are not really slowing down. This issue is complicated, no doubt at all, but Atlantic meridional overturning circulation is also a critical part of the global heat balance and important part of the Earth system, climate system, and we want to worry about it. But there are some crazy claims made about how it may collapse soon, and so on and so forth. So I keep reporting these papers just to re-emphasize the concept that this is not going to collapse anytime soon, as far as we can say. But obviously, there is a need to measure it, and then there is always a question of what can you do about it if it does look like it's going to collapse. Other than continuing mitigation, there is not really so much you can do. It's not something that I think will be fixed with some engineering solution like we are trying with corals or ice sheet, ice shelves and so on and so forth. So this paper is a modeling paper, but nonetheless it has some good messages. I'm going to be very brief. I'm not going to show any model results, and we'll just read some text. Continued Atlantic overturning circulation even under climate extremes. The Atlantic meridional overturning circulation, AMOC, vital for northwards heat transport in the Atlantic Ocean, is projected to weaken owing to global warming with significant global climate impacts. However, the extent of AMOC weakening is uncertain, with wide variations across climate models and some statistical indicators suggesting an imminent collapse. Here we show that AMOC is resilient to extreme greenhouse gas and North Atlantic freshwater forcings across 34 climate models. So we are relying on models, but nonetheless that's one of the best tools we have anyway. Those are one of the best tools. Upwelling in the Southern Ocean driven by persistent Southern Ocean winds sustain a weakened AMOC in all cases, preventing its complete collapse. So it's a global thermohaline circulation. So if you are doing something somewhere, there has to be a response on the other side for overall energy balance, heat balance, and so on. Okay, there was a Southern Ocean upwelling must be balanced by downwelling in the Atlantic or Pacific. The AMOC can only collapse if a compensating Pacific meridional overturning circulation develops. Remarkably, a PMOC, Pacific meridional overturning circulation, does emerge in almost all models, but it's too weak to balance all of the Southern Ocean upwelling, suggesting that an AMOC collapse is unlikely this century. Our findings reveal AMOC stabilizing mechanisms with implications for past and future AMOC changes, and hence for ecosystems and ocean biogeochemistry. Our findings reveal AMOC stabilizing mechanisms. They suggest that better understanding and estimates of the Southern Ocean and Indo-Pacific circulation are urgently needed to accurately predict the future of AMOC change. In other words, you have to consider the whole system and how the Southern Ocean is responding. Southern Ocean is special because it's a channel, and there are shifts in the westerlies, and there are impacts. Of course, ocean is warming, and ice shelves are sea ice are experiencing the impacts. But then, as long as the winds are there, upwelling is there. That has to be compensated by downwelling somewhere, which is the deep water formation, right? So that's the main message, and let's read a little bit about the background as well. The future state of the Atlantic meridional overturning circulation is critical for global and regional climate change, though its role in through its role in heat transport and carbon uptake. AMOC is predicted to weaken during the 21st century, driven by increased greenhouse gas concentrations and freshwater input to the North Atlantic owing to precipitation changes and Greenland ice sheet melt, which is accelerating. However, climate model projections from the coupled model and comparison project phase 6, CMIP 6, vary widely, so its future evolution is uncertain. Furthermore, there is a risk that the AMOC could collapse, causing abrupt changes in climate. Such things have been seen in the past, even recent past, small perturbations like the Younger Dryas, which we have looked at, and there may be another one at 80 to 100 years event. Several statistical indicators suggest that it is approaching a tipping point, indicating that climate models may be overstable, as AMOC changes will impact many aspects of the climate. Accurately predicting future AMOC change is vital for planning adaptation and mitigation strategies. Here we examine the AMOC's response to extreme GHG and North Atlantic freshwater forcings in CMIP6 climate models. Although simpler models and a few global climate models suggest that the AMOC could collapse, that is, weaken to zero or reverse. You have to be very careful. This is about heat transport, because as long as the Earth is a sphere and planet is rotating, there is going to be a western boundary intensification, just because the rotational effects increase with altitude. So it's a matter of the heat it carries, whether it will carry heat northward or it somehow will reverse the heat transport. Okay, some details, but it's good to be aware that there are details even if you are not an expert in the dynamics of it. Okay, here we examine that. Okay, and few global climate models. So although simpler models and so on suggest a potential reversal, it does not collapse in the model experiments considered here. Instead, the AMOC levels off at a weaker strength that varies widely across models. To understand how the AMOC is sustained under extreme climate forcing and what causes the differences in its weakened state across models and forcings, we quantify the AMOC's upwelling pathways, which return deep North Atlantic waters to the surface either through the Southern Ocean wind-driven upwelling or diffusion in the Atlantic Indo-Pacific Oceans. The Southern Ocean wind-driven upwelling rate depends on the Southern Ocean westerly wind strength that drives Southern Ocean upwelling, and on the opposing Southern Ocean mesoscale eddy response, referred to as eddy compensation. Some technical details there on how the adjustment actually happens, because this is a very, it's like a jet stream. It's a circumpolar current where it's very unstable, full of eddies, and that has an impact on how the cold waters coming up in upwelling are actually compensated in terms of where and how much downwelling is required overall. Our approach, which focuses on AMOC upwelling pathways rather than the mean state of the North Atlantic, offers fresh perspectives on the AMOC response. Although the AMOC's Indo-Pacific upwelling pathway largely controls intermodal variations in AMOC decline in realistic scenarios, the impact of extreme forcing on upwelling pathway changes, and thereby potentially AMOC resilience has not been explored. Here we assess how ocean circulation changes remote from the Atlantic affect the AMOC and its upwelling pathways in climate models. Our analysis reveals that Southern Ocean wind-driven upwelling maintains a weakened AMOC under extreme forcing, overcoming the destabilizing effects of a developing meridional overturning circulation, with the implications for understanding both past and future risks of AMOC collapse. In other words, Greenland melting, precipitation changes, freshwater forcing. Basically, I hope you already are aware of these issues. Where deep water is forming in the Greenland, Iceland, Norwegian seas and Labrador Sea, the oceans have to be salty enough. Evaporation happens, waters get denser and sink. But if you put fresh water on top, then the same amount of evaporation may not produce deep waters. So you can slow down the meridional overturning circulation. But if there is a mechanically forced part which requires sinking because there is upwelling happening somewhere else, then it's a very different mechanism. Then you have to look for overall balance as well, and not just local extreme forcings. Okay, that's the idea. And this doesn't necessarily have to happen in the Atlantic. It can happen in the Pacific with some Pacific meridional overturning circulation rising, and there is some evidence that in the past there may have been stronger PMOC as well. Okay, we define the PMOC as a clockwise overturning cell in the Indo-Pacific Ocean, characterized by sinking and densification occurring in the subtropical North Pacific and more southerly latitudes rather than the more commonly referenced northern latitudes. So these are all model dependent, so you have to be careful anyways, but the basic idea of a global balance is good, robust, and it's new as well in the way it's being detailed here. Our findings highlight the need for improved observational estimates of the Southern Ocean and Indo-Pacific Ocean overturning circulations and their heat and freshwater transports, similar to efforts in the South Atlantic. This would allow us to identify climate models with realistic present-day Southern Ocean upper cell strengths and to detect changes in the AMOC's upwelling pathways and transports owing to global warming. Constraining the AMOC's upwelling pathways would also improve predictions of AMOC weakening under realistic forcing scenarios. So even if it's not going to collapse and it's resilient enough to survive, we still need to know how much weaker it will get, because that's going to determine how much heat, greenhouse gases, and so on are going to be, even oxygen is going to be taken up by the AMOC, right? Because once it sinks and goes away, it can stay there for centuries. The future extent of AMOC decline remains uncertain, despite its critical impact on heat, carbon, and nutrient transports, and thus on global climate and ecosystems. We have shown that Southern Ocean wind-driven upwelling prevents an AMOC collapse in CMIP6 climate models under extreme greenhouse gas and North Atlantic freshwater forcings. With predicted stronger Southern Ocean winds and the present-day Bering Strait open, we conclude that a 21st century AMOC collapse is unlikely. I believe these results. However, to refine AMOC projections, a greater focus on ocean circulation changes beyond the North Atlantic and their driving mechanisms is essential. So we are obsessed with monitoring the Atlantic Meridional overturning in the Northern Hemisphere, but forgetting about the upstream drivers in the Southern Ocean and the Pacific Ocean, Indo-Pacific Ocean. Okay. We have shown that however, to refine AMOC projections, a greater focus is needed. We need to understand driving mechanisms. Future changes in both the Atlantic and Pacific overturning would impact regional weather, climate, ecosystems, and agriculture, so accurate projections of both are required to inform adaptation and resilience to climate change. This was also highlighted in a news and views kind of article. Iconic ocean current system is safe from climate collapse for now, but even a weakening of the Atlantic Meridional overturning circulation could have grave consequences worldwide. We don't know exactly but how to quantify them at local scales, but we don't want to find out the hard way, right? So there is another article on the same topic, but this has a bit more detail, so I'm going to read. So it explains the model experiments a bit better, so without looking at the technical details we can still learn a bit here, because this is written for non-experts. A system of ocean currents called Atlantic Meridional overturning circulation strongly affects climate, but is showing signs of shutting down. The wording is not really so good. An analysis now suggests that the total collapse is unlikely this century, which is what we already said. A system of currents known as AMOC, and it will not completely shut down even under extreme conditions, but the mechanism that prevent a full collapse have been unclear. Here, the paper we looked at finally identifies the AMOC stabilizing mechanisms through an analysis of simulations using several climate models, bolstering the understanding of the key processes that affect the resilience of the AMOC to a warming world, which is new. That's why it's interesting to report on this. The AMOC consists of two main components. A warm and salty flow of water travels northwards through the upper layers of the Atlantic Ocean before sinking to the deep ocean in the subpolar North Atlantic. So we'll look at that here. So there is sinking here. Warm salty water is this upper branch, which is basically associated with the mixing bowl here, the inundation of the deeper waters that get converted to surface waters and eventually make it back through the Indonesian seas, also an upwelling branch in the Indian Ocean. They get together. There is some retroflexion and there is some outflow. So this is the deep water forming blue pathway, sinking and coming south. And there is also some sinking happening here in the Southern Ocean. Ross Sea, Weddell Sea, they all mix together and inundate here, and they are showing a downwelling branch here. So this is a sinking branch, upwelling branch, and a downwelling branch. And this is in the strong AMOC case. In the weak AMOC case, you would reduce this sinking, which is potentially already happening, even though it's hard to confirm it because we don't have direct measurements. And then you would have new ways of compensating for the upwelling that will continue here, and that is by downwelling in these places in the so-called Pacific Meridional overturning, as opposed to all the sinking just happening here to compensate for the upwelling here. Okay, so this is kind of a good schematic to keep in mind as we read a little bit more here. The AMOC consists of two main branches, as we said, the deep water forming in the North Atlantic and the resulting deep water flowing southwards, eventually welling up to the surface in the Southern Ocean and Indo-Pacific Oceans. Baker et al., the paper we looked at, analyzed simulations from 34 climate models to assess AMOC's stability in two extreme scenarios. In the first scenario, atmospheric levels of carbon dioxide have quadrupled compared with pre-industrial levels, so 280 ppm to 280 times 4. And in the second, a large amount of fresh water has entered the North Atlantic, as would occur with melting of the Greenland ice sheet. The authors find that in all models the AMOC weakens but is sustained by upwelling in the Southern Ocean driven by strong winds in that region. So to the extent that these models are able to capture the impact of changes in the North Atlantic deep water formation on the winds in the Southern Ocean winds and upwelling will continue, which means compensating downwelling will continue, with a potential mechanism in the Pacific that could keep the sinking going but can maintain it at a much weaker state. Okay, to understand to understand the AMOC sustaining mechanism proposed by Baker et al., consider an analogy in which a tank contains all of the water in this circulation. Water enters the tank from an inlet, which represents the sinking water in the subpolar North Atlantic, and water exits through two outlets, which represent the upwelling in the Southern and Indo-Pacific Oceans. To prevent the tank from overfilling and emptying, the amount of water flowing in must equal the amount exiting. So there is some time scale involved because the real world ocean is so big. This means that when the flow entering the tank decreases, and analogous to a weakening of the AMOC, then water must exit through the two outlets more slowly. Baker and colleagues suggest that the water upwelling in the Southern Ocean cannot slow down because it's driven by persistent strong winds. In the tank analogy, this equates to one of the outlets pumping out water at the same rate regardless of the amount of water coming in which would cause the tank to empty if the inflow of water decreases. In that scenario, one way to prevent emptying is to reverse the flow of water at the second outlet. That is, this is what Baker et al. Observed in climate models. A circulatory system develops in the Pacific that feeds the deep water into the Southern Ocean. Okay, so that's what we mean by downwelling here. So instead of just water coming from here and upwelling and going back, with some downwelling here in the strong AMOC case, in a weak AMOC case, this may reduce, but this still continues to pull up water, so you have to put down water somewhere else, and that's going to happen here. Okay. Okay. In the tank analogy, that's what happens. In that scenario, one way to prevent emptying out. So, however, the secondary source of water is too small to fully compensate for the reduced inflow from the subpolar North Atlantic. The requirement that the upwelling in the Southern Ocean must be balanced by downwelling in the Atlantic or Pacific means that downwelling in the subpolar North Atlantic cannot completely shut off, preventing a full collapse of the AMOC. So, you can think of the water coming in from the inlet, like the water sinking in the North Atlantic, which we assume is controlled externally, independent of having to compensate water coming out here or in the Pacific. But if this keeps on demanding that water be pulled up, then tank is not to get empty. Then there is a pull on the water to sink, and that downwelling is now somewhat mechanically forced, as opposed to just kind of this kind of a balance. So here there is a balance. There is I'm not going into details, but there is a long-term circulation with water sinking here, upwelling everywhere and coming back, but you change those strengths of upwelling to remain the same. This is to weaken, then that means you will strengthen this, but this cannot get strong enough in the climate for the next 100 years. So this is mechanically being forced to still sink some water. Okay, and that's the way you can think of it. On the basis of their analysis, they conclude that the likelihood of total AMOC collapse in the 21st century is extremely low. This finding contradicts those of several studies that use statistical analysis of observations and simulations of the AMOC. However, climate models are not perfect representations of the real world, and However, climate models are not perfect representations of the real world. And it has been suggested that they might overestimate AMOC stability. Baker and colleagues argue that AMOC stability is not overestimated in climate models because it is associated with persistent southern ocean winds that might actually strengthen slightly in a warmer climate, and even if the flow of deep water from the subpolar North Atlantic becomes insufficient to support upwelling in the Southern Ocean, deep water will instead form in the Indo-Pacific. Okay, so just to read a bit more, another factor that might prevent complete AMOC collapse is melting of the Antarctic ice sheet. When the resulting meltwater flows into the ocean, it leads to a decrease in the formation of Antarctic bottom water, which is the heaviest of the waters sinking, and the densest water in the world, which forms when salty waters at the surface of the Southern Ocean cools and sinks to the seafloor. But that bottom water formation is reduced by, if it is reduced by the influx of meltwater of the Antarctic, then the sinking of water in the subpolar North Atlantic will increase slightly to compensate, stabilizing the AMOC. So now we are getting into heuristic arguments, but it should also be noted that AMOC weakens in all of the climate models that Baker et al. Used. The development of circulatory system in the Pacific Ocean cannot fully compensate for the weakening. Moreover, the upwelling from Southern Ocean remains relatively unchanged, whereas combined sinking in the Pacific and Atlantic reduces, leading to an overall reduction in the deep water formation. To maintain the balance between sinking and upwelling, contributions from other sources of sinking water, such as the southern subtropical oceans, are required, which might not be directly related to AMOC. This might imply that sinking in the subpolar North Atlantic is an essential factor for controlling AMOC's strength. Okay, so does Baker and colleagues' conclusion that the AMOC will only weaken rather than collapsing completely mean that it is no longer necessary to worry about the AMOC in the context of climate change? Unfortunately, not, because heat transport into the subpolar North Atlantic and surrounding regions is proportional to AMOC strength, and even just a 50% reduction in the strength would result in a large drop in heat transport that would alter regional and global climates. There is therefore no reason to be complacent about the AMOC weakening, and every effort must still be made to combat the global warming that drives it. Okay, that makes sense. So essentially, we are just trying to put a finer point on the claims based mostly on some models and statistical analysis that the AMOC is imminently going to collapse, and say that maybe not so soon, but we still have to worry about its slowing down. Scientifically, it's important to nail down whether it will collapse or not, because that is a science question beyond all the impacts and actions needed, because for such a large global circulation, actions still just come down to continued mitigation and not taking our eyes off on mitigation, which is anyway needed, right? So let me leave this here.